Let's look at how we can apply transition state theory to calculate rates and pre-exponential factors for different physical situations. Our starting point will be that we can write the reaction rate constant as Boltzmann's constant times temperature divided by Planck's constant times the partition function for our transition state with one mode removed, which is the vibration along the reaction coordinate. So that's taken into account by this term kt over h, divided by the product of the total partition functions for our reactant states, which I'll just label I here. This is all multiplied by e to the minus activation energy over kBt. This takes into account the difference in ground state energies between our reactants and our transition state. So let's look at the adsorption of an atom A onto a surface to form a mobile adsorbed species. And let's attempt to calculate the pre-exponential factor that we would expect from transition state theory. So the physical situation is pictured here. We have A that can move around freely in a fluid or gas phase. It's approaching the surface to form some transition state at some point, and then finally it forms an adsorbed species which can move around freely in 2 dimensions. So if we want to calculate the pre-exponential factor A, that will be equal to this term here. And so our goal will be to write the partition functions for our transition state and for our reactants. So which partition functions do we need to consider in this case? So we can write the total partition function as the product of the partition functions associated with translational modes, vibrational modes, rotational modes, and electronic states. So we'll generally assume here that the electronic contribution is negligible. So let's consider these other modes. So if we have an atom A in the gas phase in our reactant state, we're not going to have any rotational modes or vibrational modes available to it. So all it's going to have is translational degrees of freedom in 3 dimensions. For our transition state, again, we're not going to have any rotational modes. We will have one vibrational mode, so we can picture this here. So if this is my molecule A approaching my surface site, I'm going to have this vibrational mode between the, say, metal atom and A, but this is exactly the vibration along the reaction coordinate, which we've taken into account with this term kt over h, so it's not going to appear in the partition function for our transition state. So that's why we label this partition function prime. We're going to have only partitional functions associated with translation for both our reactant A and our transition state. So we can write the total partition function for our reactant A. So here we're going to have 3 translational degrees of freedom, and so we can write the translational partition function as 2 pi times the mass of A times Boltzmann's constant over temperature divided by Planck's constant squared. And so this is raised to an exponent that depends on how many degrees of freedom that we have. So it's raised to the 1/2 for each translational degree of freedom we have. In this case, it's going to be raised to the 3/2 power. So this numerator here tells you the number of degrees of freedom for translation. So for our transition state, this is going to be confined to the surface, so it can move freely in 2 dimensions. So it's going to have 1 less translational degree of freedom than our reactant state. So this expression is going to look identical, except it's going to be raised to the 2 over 2 power, or just simply the first power, instead of the 3/2 power. So we can use these partition functions to write our pre-exponential factor. It's going to be equal to kt over h times 2 pi times the mass of A times kBt over Planck's constant squared, and this is raised to the minus 1/2 power, since the partition function in our numerator of the transition state had a power of 2 over 2, and the partition function for our reactant state in the denominator had a power of 3 over 2. So simplifying this, we get an expression for our pre-exponential factor that's the square root of kBt over 2 pi times the mass of A. So these are all known constants, and we can get a quantitative result for the pre-exponential factor that we would expect for this physical situation. So what if the adsorbed species is not mobile? So here again, nothing has changed for our reactant species. We have 3 translational degrees of freedom, but now we have no translational degrees of freedom for our transition state. So since the partition function for the transition state only had modes associated with translation available to it, the partition function here for transition state is just going to be equal to 1. So we can write our pre-exponential factor for this case as kt over h times 2 pi times the mass of A times kBt over h squared, and this will all be raised to the minus 3/2 power. So simplifying this a bit comes out to Planck's constant squared divided by kBt to the 1/2 times 2 pi times the mass of A to the 3/2. So here in this case, since we had a partition function greater than 1 in our numerator for a transition state, and now we've replaced it with 1, you can see that the pre-exponential factor for the mobile case is going to be significantly larger than the pre-exponential factor for the immobile case. So we can also interpret this physically from a thermodynamic perspective, remembering that we can write the pre-exponential factor as kBt over h times the exponent of the entropy of activation divided by the gas constant R. So for the immobile adsorbed species, more entropy is lost upon adsorption, so A is smaller. So these are just a few simple examples of how transition state theory can be applied to calculate elementary reaction processes.